So in this example problem, we're going to draw another shear and moment diagram for this beam that's shown below. So in this beam we have a pin at point A, and we have a roller at point B, and then we have a distributed load of 4 kilonewtons per meter from point B to the end of the section. So the first thing we need to do is we need to find the reaction forces. So we need to find A of x, A of y, and B of y. So if we draw our free body diagram of our beam here, we end up getting A of x, A of y, and B of y. Alright, those are our reaction forces. Then we have our distributed load of 4 kilonewtons per meter along the rest of the beam. We know that it's 4 meters from point A to point B, and we know the rest of the beam's length is just 2 meters. Okay. So if we sum all of our forces in the x direction and set that equal to 0, we just have A of x. Therefore, we can say that A of x will be equal to 0. Alright, we can then sum all of our forces in the we can sum all of our moments about point B and set that equal to 0. If we do that, we would end up getting A of y times 4 meters. It should be actually a negative moment. So it'd be minus A of y times 4 meters minus 4 kilonewtons per meter times 2 meters times 1 meter. So the area under our distributed load would be our concentrated force. So that's our 4 kilonewton meters times 2 meters. And then the centroid of our distributed load would give us our moment arm of 1 meter. Alright, so if you rearrange this and solve for A of y, we get A of y is going to be equal to 4 kilonewton meters times 2 meters times 1 meter, which is just 8 kilonewton meters, or minus 8 kilonewton meters, divided by 4 meters. So we're going to get minus 2 kilonewtons for AY. Alright, to solve for B of y, all we're going to do is we're just going to sum all of our forces in the y direction and set that equal to 0. If we get that, we will get B of y minus 2 kilonewtons minus 8 kilonewtons. So B of y is going to be equal to 10 kilonewtons. Alright, cool. Alright, so once we have our 3 reaction forces, the second step we have is we'll have to draw a shear diagram. Alright, so positive forces will be on the top, negative forces will be on the bottom. So we know that for concentrated loads, we know that the change in V will just be equal to the concentrated force. So we have A of y is equal to minus 2 kilonewtons. So we would have we have a force of minus 2 kilonewtons be applied at x is equal to 0 meters. Alright, and then there's no applied loads at all from point A to point B, so we would just have a constant value of shear, so V of x is just going to be equal to minus 2 kilonewtons from x is 0 until it gets to 4 meters. Then at 4 meters, we have a concentrated force again. So for a concentrated force, we know that we just add that force to our free body diagram. So we know that B of x is equal to 10 kilonewtons along this region. So we would have plus 10 kilonewtons. So we go from minus 2 to 8 kilonewtons at x is equal to 4 meters. Alright, and then we know for the rest of our diagram, we know that m of x is going to be equal to the value of m of x at x is equal to 4 meters, so that would be equal to 8 kilonewtons, plus our change in our moment. So our change in our moment is going to be equal to our integral, our shear force is going to be equal to 8 kilonewtons plus delta V. Alright, so delta V is going to be equal to the integral from our starting location 4 meters to x. Alright, and then we're going to have W of x dx. Alright, so we would have our delta V is going to be equal to W of x in this case is just equal to minus 4 kilonewtons per meter times, which is a constant, dx. Alright, if we perform that integral, we end up getting minus 4 kilonewtons per meter times x from x to 4 meters. So we get minus 4 kilonewtons per meter times x minus 4 meters. Alright, and that's our delta V. So we can plug that into our equation here. Alright, so our equation here ends up being V of x is equal to 8 kilonewtons plus, minus 4 kilonewtons per meter times x minus 4 meters. Alright, and then our last one we have is we can draw our moment diagram. Alright, so we have our moment of x, we have our negative moments or our clockwise moments along the positive axis, we have our counterclockwise moments, our positive moments along the negative y-axis, and then we have we're going to draw our 3 important locations again: 0 meters, 4 meters, and 6 meters. So we know that m of x is going to be equal to our moment at x is equal to 0. So if we have any concentrated moments plus our change in moment, since there's no concentrated forces at point A, this will be equal to 0. So m of x would just be equal to delta m, which is just equal to, earlier in the packet we defined it as being equal to v of x dx from our 2 points of interest, which are 0 and x in this case. So we have v of x we defined earlier as being equal to just minus 2 kilonewtons dx. Alright, so we're going to end up getting minus 2 kilonewtons x from x to 0. So we're just going to get minus 2 kilonewtons x. Alright, from 0 meters to 4 meters. Alright. So at the end of this, we'd have minus 8 kilonewton meters would be our moment at 4 meters. All right, so we just have a nice straight line along here. All right. And then from the rest of our beam, we have m of x is going to be equal to our moment at 4 meters. So I'm going to say moment at x is equal to 4 plus delta m. All right, so we know that m of x will be equal to minus 8 kilonewtons meters plus delta m. So we know delta m is going to be equal to, we're going to integrate from 4 meters to x, and then we have our v of x that we had earlier. So we're going to have, say this is our equation here. So we have 8 kilonewtons minus 4 kilonewtons per meter times x minus 4 dx. All right. So so if we do this integral, what we end up getting is we get minus 8 kilonewtons meters plus 8 kilonewtons x times x, and then 4 meters minus 4 kilonewtons per meter times x minus 4 squared, from x to x is equal to 4 meters. So if we evaluate these integrals or these equations, what we end up getting is minus 8 kilonewton meters plus 8 kilonewtons times x minus 4 meters minus 4 kilonewtons per meter times, when we plug in x, we'll get x minus 4 squared, and then we'll get minus 4 kilonewton meters times 4 minus 4 meters, which is just 0. So this term, we'll just get rid of it. All right. So if we wrote all that out, what we could end up getting is, if you resolved all this out, all these equations out, you should end up with minus 2 kilonewtons per meter times x minus 6 meters squared. All right, so this is again a negative parabola. If you plug in x is equal to 4, all right, you would end up with minus 2 kilonewtons per meter times minus 2 meters squared. So you end up getting minus 8 kilonewton meters, right, which is good. That matches what we had on the other side. And then at x is equal to 6 meters, you would just get 0 kilonewton meters, which makes sense. The total applied couple moment in this situation should end up equaling 0 at the very end. All right. So the one thing I like to point out here is that the area that we have drawn under these curves here, so I'll highlight this area here is equal to, or I should say, the area under here, I should say, wrong area, this area, all right, is equal to the moment at x is equal to 4. All right, so we had minus 2 kilonewtons times 4 meters is equal to 8 kilonewton minus 8 kilonewton meters, which we have here. All right, and then if you look at the area under this triangle here, all right, that's equal to, I'll call this A2. All right, that's going to be equal to 1/2 times the height times the base. So we had the height of that triangle is equal to 8 kilonewtons, and the base is equal to 2 meters. So that's equal to 16 kilonewtons divided by 2, or is equal to 8, positive 8 kilonewton meters. So if you added 8 kilonewton meters to minus 8 kilonewton meters, you know that you get our total result, which would be equal to our moment of 0 kilonewton meters at x is equal to 6 meters. All right, so you can use the areas of underneath the shear diagrams to help you draw your moment diagrams. The only thing is that these will not account for any couple moments in your system. All right. So to conclude the problem, to summarize the problem, we found our reaction forces using the equilibrium equations. Once we had our reaction forces, we drew our shear diagrams. Okay, using our shear relationship, which we have as being equal to the shear at the starting point plus the integral of w of x dx from our starting point to our end point. All right. Once we have those equations across our beam, we can then draw our moment diagram using those relationships and this equation here. All right, so that concludes this problem on drawing shear moment diagrams using the relationship between the distributed load, shear, and moment.